Hi guys, and welcome to another flip lesson. Today we're going to be learning about page 10 of the Earth Science Reference Table. This is the inferred properties of Earth's interior chart. We say inferred because we infer this. This is based on evidence that we have found from earthquake waves. So that's actually how we have all this information. Essentially what we've done is we've looked at seismic data, and seismic data tells us about what the Earth is made out of. Now, basically what's going on here is this understanding is necessary so that you can have a better idea of what's going on underneath Earth's surface. So, for example, plate tectonics, continental drift. How are we going to understand plate boundaries unless we understand what a plate is, what part of the Earth it is making up, and what is beneath it, what is it riding on top of? So let's dive right in. First, let's take a look at the density of the different layers of the Earth. Well, as you increase depth within the Earth, what happens to density? It's increasing. You're starting with 2.7 and 3.0. That's to represent the difference between the continental and oceanic crust. Then we're looking at 3.4 to 5.6 grams per centimeter cubed. It says it right here. For the mantle overall, so that's both plastic and stiffer mantle. And then we're looking at outer core and inner core as higher as well. What are they made of? So composition, inner core, iron and nickel. Those are some heavy metals. So during Earth's formation, they sank deep within the Earth. Outer core, guess what? Also iron and nickel. And we'll come back to the outer core and its special properties in a little bit. Well, now we want to look at depth within the Earth. How deep does the Earth go? So actually, all of the layers that we see that we're looking at right now, so everything here actually can be found below it if we follow along the graph that is designed for us here. So for example, we're just going to focus on this layer right here, which is the asthenosphere. Let's follow that layer down and see how deep within the Earth it goes. So we're going to continue to follow it down this way so we can still see that green that we drew up here. Follow it down, follow it down, follow it down, and eventually we're going to get down here. This chart represents depth. Let's take a look a little closer. Here we go. Represents depth. So essentially, the asthenosphere is whatever this number is, so maybe 100 or so kilometers, all the way up to, let's find where it stops, maybe right around here. So to me, that looks like maybe about 600. So if I was getting the depth of the asthenosphere, I would say it would be between 100 to 600 kilometers of depth. And this is just showing the depths of the different layers based on these dotted lines that we have in front of us. Well, let's do something a little differently here. Okay? Let's look at depth for whatever this layer is, and we'll figure out what the layer is. So, first, it's a little below 3,000, so the depth of this layer goes from about 2,900 kilometers all the way up to, it looks like it's just beyond 5,000, so I'm going to call that 5,100 kilometers. Okay, just an example. All right, well, now let's go follow it back up and see where it matches up. Back up top. These were the lines we were dealing with. We had this one and this one. What are we measuring? The outer core. So all we're trying to demonstrate here is that all of these layers are represented by the dotted lines that you guys see in front of you now as you move down the chart. What's interesting is they can tell us about the pressure and temperature as well as the state of matter for every layer. We're going to start with pressure. Pressure is probably the easiest one. Check out pressure here. It's measured in, as it says here on the side, millions of atmospheres, very often abbreviated MATM. Okay, an atmosphere is a measurement of the average atmospheric pressure at Earth's surface. So, the boundary between the stiffer mantle and outer core is represented by this line. If we want to know what the pressure is within the Earth, all we need to do is follow that line down until it hits the index curve, and then follow it over to the axis. So, what is the pressure right between the stiffer mantle and outer core? It's right about here. Looks like to me about 1.5 MATM in this case. Okay, let's try an example for temperature. So we're going to do the same thing with this boundary between the stiffer mantle and outer core, and let's follow it down. So it's represented again by this same dotted line, and then it's going to hit the index curve right about here. Well, we want to know what the temperature is for that, so we're going to follow it over across. Looks to me like it hits just below the 5,000 line. I'm going to call that 4,900. 4,900 what? It says it right here, degrees Celsius. So this is how we get temperature. This is how we get pressure for the different parts of this chart. Let's try something different. If you've ever heated anything up and wanted to melt it, for example, ice. The only way to melt ice is for you to heat it up so it reaches, hits, and then gets beyond, higher than its melting point. Melting point and freezing point are the same number. It's just a matter of whether you're heating or cooling. So let's say we take a piece of ice and we're heating it up. If you want to heat up a piece of ice, here's my representation of a piece of ice. If we're going to heat up this piece of ice and we want it to melt, well, we're going to have to get it above 32 degrees Fahrenheit, also known as 0 degrees Celsius. So let's say that line, we're going to represent it visually here with this black line. If this is the 0 degrees Celsius line, and I have H2O that is higher than, the temperature is higher than that 0 degree line, guess what? It's definitely going to be a liquid. Why? Because we heated it up past its melting point. So since it's higher than its melting point, it's melted to water. If we have H2O that is below the temperature of 0 degrees, below its melting point, below its freezing point, well, it's always going to be a solid because we've cooled it beyond its freezing point. Now I bring this up because when we look at this chart, it's going to matter. Let's take a look, for example, at the inner core. We're going to pay very careful attention to this. The dotted line represents the melting point. The melting point, the temperature at which the material within the Earth would melt. Interior temperature, this is the actual temperature of the material. Well, in the Earth's interior, in the most deepest part, in this case the inner core, the temperature line is below the melting point line, which means the temperature is less than the melting point. So has it heated up enough to exceed the melting point and melt? No. So this is going to be a solid. The inner core is a solid. But there is one layer of the Earth for which this is not true, and that is going to be the outer core. If we look at the outer core here, the melting point is below the temperature, meaning that it's gotten so hot in the outer core that the outer core has exceeded the melting point for this temperature and pressure and the type of material that's there. So the outer core is actually a liquid. I'll leave you with one last thing in this department, and it's an important thing to take home. There is partial melting right here. This is known as the asthenosphere. Now, what does that mean? The asthenosphere is a very special substance. Essentially, the mantle that is there is a solid that acts like a liquid. We would call that a semi-solid. It flows like a fluid. The material there moves. When it's heated from below, it rises, and then it cools to form what's called a convection cell, which we will talk about a great deal in class. But the point of today was simply to point out that, hey, we have different layers of the Earth. They have different depths, pressures, temperatures, and states of matter, and we need to be able to calculate those. I hope that this lesson has been helpful to you. Please do the work that's